Good morning, student. Welcome to join our class again. This is lecture 9 for our module theory of structure tools. I think that this is the lectures right before our quiz, right? Next week we will have a quiz during this period. Next week, next Friday. I will give you some tips later today. But at the beginning, let us continue our lecture material first. I will mention something about the quiz at the middle, because I believe that more students will join later. So before starting the class, maybe you can have a look of Moodle. At the same time, we can wait for more students to join. This is the page of our Moodle. I have just uploaded something on Moodle. Firstly, I uploaded the STEP 2000 assignment. Firstly, I uploaded the grade of assignment 1. You may check your grade of assignment 1 in Moodle under the icon grades. The full marks is 100. And then I have uploaded STEP 2000 assignment on Moodle. Here, yeah. This is an individual assignment. What you have to do in this assignment naturally is just similar to what we done in our workshop. You build a model, calculate the torque drift, calculate the moment find out the moment diagrams, and find out the mode shapes, modal frequency. Exactly similar to what we did in our workshop 1, workshop 2. I've also uploaded a video for workshop 1, workshop 2. If you like, you may also have a look of the videos. The deadline of STEP 2000 assignment is before the end of this module, before the end of this semester. So you still have some time to finish it. It's quite easy if you understand what we did discuss in the workshops. Actually, I believe that it takes you around 30 minutes to 1 hour to complete this assignment, STEP 2000. Pretty straightforward. Last time, some students asked for the equation sheet. I also uploaded the equation sheet for our quiz. And then another bad news is that I also uploaded the assignment 2 on Moodle. In this module, I have only 2 assignments for you, excluding the lab report, excluding the STEP 2000 workshop. Okay, there are only 2 normal assignments for you. This is the assignment 2 for related to structural dynamics, particularly for single degree of freedom system. I will also talk about assignment 2 later, because I believe that more students will join later. Same reasons. You can find assignment 2 right here, at the middle of this page, particularly related to single degree of freedom system dynamics. Not very difficult because this one not much matrix, no matrix for assignment 2. Basically, just like the example that you found in the previous tutorial, for structural dynamics single degree of freedom system, normally it just takes you 1 or 2 equations to complete the calculations. If you understand, if you can identify which equation to use. There are many equations for free vibration, harmonic vibration, forced vibrations. We have to select the appropriate equation to use. Then it's pretty straightforward. Hopefully today we can complete all the things for structural dynamics, single degree of freedom system. We will start from topic 7 today, the last part for single degree of freedom system. And then we can move on to multiple degree of freedom system today. I also think that we can complete topic 8 today, and hopefully we can go to topic 9 if possible, if everything runs smoothly. So as usual, before beginning our lecture materials, is there anything you want to ask me? Okay, thank you for your response. If no, then maybe we can start right now. We will start from topic 7 today. Let me share let me share the screen with you. Topic 7. In this topic, we are going to discuss very general approach to analyze the response of single degree of freedom system under arbitrary load. We call this method as numerical method, a very general, powerful method to handle all kinds of loadings. Last time in topic 6, We introduce four-step ribations. We introduce how to analyze the structures under harmonic ribation, under a pulse. That kind of equation are useful particularly for some special case. But what happens if the structures is under arbitrary loading? We will discuss how to do it in this particular chapter, topic 7. This is the content page. At the beginning, we will introduce the background informations, the general idea, and then I will introduce 2 specific methods, central different methods and Newmark's method, how to analyze structures under arbitrary loading. They simply based on different assumptions. You will know very soon what they. In fact, there are many methods under numerical methods. I just select 2 classical methods here for introduction purpose. Firstly, let us have a look of the background information, what is so-called numerical methods or time-stepping methods. Well, so far, we analyze a single degree of freedom system under different kinds of loadings and a few types of loadings. Say, for example, we have learned how to analyze structures under free ribation, in which the force is equal to 0, right? And then we learned this in chapter 5. And then in chapter 6, we learned, firstly, how to analyze structures under a side loading, a sinusoidal force. And then we learned how to analyze a structure under a pulse loading. A pulse loading, there is no simple math function, right? A pulse loading. At that time, we can express our loading precisely in terms of some mathematical functions, a sine function, cosine function, etc. For this case, if you can express the loading precisely using a math function, then you can solve for the closed form solution for our displacement U. That is what we learned in topic 5 and topic 6. You can get the analytical solution. You can get the closed form solutions if the loading is a well-defined loading, simply speaking. But what happens if the loading is not well-defined? If you cannot express the loading precisely using some simple math function, then you can't solve it. Just like this equation, right? This is well-defined loading, a sine loading. You can find out the closed form solution. I hope you still remember the solution for this form, for this equation. We introduced in topic 6, right? The steady state response is equal to UST times RD times an oscillating function, psi something, right? A steady state solution for a harmonic ribations we learned in topic 6 at the beginning. But if you cannot express the loading clearly on the right-hand side of the equation, just like the picture on the right-hand side, you cannot find out a simple math function to represent this loading, right? It's not a sine, it's not a cosine. Yeah, it's quite difficult to express these functions, this loading into a functions. So if right-hand side is not a simple math function, then you cannot find out the solution for this problem. So in this chapter, we will discuss how to consider how to find out the response for structures under arbitrary loadings. Well, actually, if you remember, last time in topic 6, we actually introduced another approach to handle this kind of arbitrary loading. We call it the Duhamel integral, right? The Duhamel integral. But here we would like to introduce another approach, rather than based on pure theory. We based on some approximation, which can also help us to evaluate the response of structures under arbitrary loading. The Duhamel integral is nice, but it's quite difficult to find out the integrations of that complex functions. So what we're going to do right here, we are going to adopt an idea called time-stepping method. Say, for example, if you have a loading history as shown at the bottom, you can divide the loading history into different time steps. At the beginning, time equal to 0, t0, normally it is equal to 0 at time at the beginning, right? And then T1, T2, T3, T4, T5, and so on. And then one arbitrary time instant is Ti, Ti plus 1, etc. You can divide your whole loading history into different finite time steps. Normally, we will set the time interval equal to delta t. And normally, we set delta t as a constant. Say, for example, delta t is equal to, say, for example, 0.1 second. If delta t is 0.1 second, means the time increment is equal to 0.1. Okay, 0, 0.1, 0.2, and so on. The time step, the time interval, the time step, or you may call it time step. The time interval or time step is depends on your choice. You may set this equal to 0.1, 0.2. If you want to get more accurate result, then you can set it smaller, 0.01, 0.001, etc. So it depends on your decisions. So here we cut the loading into different time instant, and then we consider our equation at each time instant. This is the general equation of motion. Okay, this is general equation of motion we derived together in topic 4. This equation is true along the whole time history, which means that this equation is true at time equal to 1, time equal to 2, time equal to 3. All time instant, this equation should be satisfied. So you can see that at one arbitrary time instant, time t, you can also express time t using this equation. You express in terms of the acceleration at time step ti, velocity displacement at time step ti. Okay, you can substitute the values at this time step into this equation. It's also true. So it's helped us to handle this arbitrary loading, because when you take a look on the picture at the bottom, you cannot find out one simple function to represent the force P, right? But you can find out the coordinate at each time instant. You can find out P0, P1, P2, P3, P4, etc. Right? You cannot find out the math function, but you can find out the coordinates at each time instant. And then you just simply substitute the values of the loading at each time instant into the equations. So here you will have n set of equations, time t0, t1, t2, ti plus 1, and so on. You will have many equations of motions. Once you solve all the equations, then you can get the whole displacement history of the structures. That's why we call the time stepping method. We do it step by step along the time domain, from the beginning and then up to your target time instant, time t or I plus 1. Normally, you firstly find out what happened at the beginning and then use the result to predict what happened on the next. Solve for displacement, velocity, acceleration, etc. Time stepping method. Give me one example. You try to find out what happened at time equal to t1 here. To solve this equation, you need some initial conditions, just like free vibration. We have initial displacement, initial velocity. You should know what happened at the beginning of the structures at time equal to 0. They are initial conditions. So you can use some method to solve this equation. Not easy, but at least it's solvable. What I can say is that this one is solvable. If you have some additional informations, then you can solve it. Solve for displacement, solve for velocity, solve for accelerations. So equation 1 is okay, solvable. After solving the first equation, you can jump to the next time step, T2. At time step 2, at this moment, you know U1, you know velocity 1, because they are solved in the previous equation, right? You have at times 2, you has already evaluated what happened at time T1. So you can use the response at time T1 to predict what happened at time T2. Okay, that is what I mean doing step by step. You have to start from time equal to 0, T1, T2, T3. The previous response can help you to predict what happened on the next. So you can put down the equation for T3, T4, T5 up to Ti. Okay, this is the basic idea of time stepping method. The concept is quite easy because it just do step by steps. But what I mentioned here is that you need some additional information. To be honest, you need some additional information in order to solve these equations. You cannot easily solve it directly. You need some additional approximations. Okay, you have to make some approximations. That's why at the beginning you have seen that there are different numerical methods, Newmark's methods, central different methods. They're actually based on different assumptions, different approximations. But here I show you the general idea of time stepping methods, do this step by steps. Some textbooks call this time history method, time history analysis. Time history analysis depends on the terms that you call it. We have different numerical methods. We have different time stepping methods. We have interpolation, we have central difference, we have Newmark's, we have Wilson beta, we have many time stepping methods. In this module, we just pick 2 classical methods for discussion purpose. But when you read the textbook or when you search in the internet, you can find out many numerical methods, more than these 2. Okay, but we just introduce the background to let you know what is so-called time-stepping method. This kind of method is quite powerful because you can use it to predict what happens for structures under almost any kinds of loadings. You can use it for sine loading, cosine loading, okay, pulse loading, okay, arbitrary loading, also okay. So very powerful. Let us begin with central difference method to see what they are. You can taste the beauty of numerical methods. As mentioned before, when you want to use this kind of method, you have to divide the whole history into different time steps: T1, T2, T3, etc. Here, I just showed you 3 arbitrary time steps. They are so-called T-1, Ti-1, Ti, and Ti+1. I just showed you 3 arbitrary time steps. This is the displacement time plot. Suppose we have some discrete point for the displacement. So what is this method? Central difference method. Central difference method based on one assumption called finite difference approximations. What is finite difference approximations? Go back to our calculus. Velocity. By definition, velocity is equal to what? Equal to du dt. Rate of change of displacement give you velocity. But you can express du dt approximately using the difference of the displacement. Maybe I call this u2 minus u1 over the difference in the time, which means delta t. So if you know the displacement before and after, taking the difference and then over delta t, then it becomes the approximate value of velocity. Okay. Instead of solving this using calculus, you can use this kind of finite difference approximations to estimate velocity or acceleration. This is the basic background of central difference method. Instead of considering calculus directly, here we use this kind of finite difference approximations. Use the difference in displacement, difference in velocity to estimate velocity and accelerations. That's why we have these 2 approximations. First one. U dot mean velocity at time step 1 as time step I is equal to the displacement at time step I+1 here minus time step I-1 and then over 2 times delta t because we pass through 2 data points. So here show you the approximate values of velocity. Similarly, acceleration can be expressed using, actually this one is derived from ui plus 1 minus ui and over delta t. This is the velocity. This is the velocity before the time step under considerations, and then minus the velocity ui minus ui-1 over delta t. This is the velocity before, right? The velocity after minus the velocity before the time under considerations, and then over delta t. That's why you have delta t squared in the denominator. And then after doing some simplifications, you can get this approximate formula. Acceleration u double dot I is equal to the displacement ui plus 1 minus 2 times ui plus ui minus 1 over delta t squared. This is so-called the different approximations. No calculus involved right now, just depends on simple addition, subtractions, and divisions, right? The beauty is here is that displacement, velocity can be described using displacement. Acceleration is also described only using displacement u. There is no velocity involved in the equation right here. Now you can substitute these finite different approximations into our equation of motion again. Velocity and acceleration can be replaced using these finite different approximations. U double dot I is equal to this one. UI dot equal to this one, right? And the whole equation is now involve only displacement, no velocity, no acceleration terms. And then we can rearrange this equation a little bit. Say, for example, we can move ui plus 1 on one side, move the other item on the right-hand side. You can slightly manipulate this equation, move ui plus 1 on one side, and then move the other items on the right-hand side of the equations. Please note that ui minus 1, they are the response that in the previous time step. And now we are going to find out what happened on the next ui plus 1. So ui is known. Ui minus 1 is also a known value. You can use these two known values to predict what happened on the next steps. This is the background of this central difference method, using previous response to predict what happened on the next. And then it's relying on this approximation, 5 different approximations. Replace velocity, acceleration to using displacement. After some operations, we can find out these equations. We just move ui plus 1 on the left-hand side, move the other item on the right-hand side. That's it. No special things we did here. We just slightly rearrange the arrangement of these equations. And then we do some grouping. Say, for example, I group the coefficient before ui plus 1 into a terms called k with a head on the top, k hat. And then we group all the things on the right-hand side to another coefficient p with a head on the top, right, p hat. I just grouping these terms together to make the equation look slightly simply. So you can see that ui plus 1 is equal to p hat over k hat. Okay.
Thank you.
Oh. Here I show you the definitions, k hat and p hat. M is mass of the system, suppose you know it. C is the damping coefficient, you also know it. MCK, you know MCK, the three fundamental dynamic properties. Loading, you also know the loading. You know the loading. You cannot express the loading mathematically, but you know the coordinate at different time instant of the loading. So PR is also well defined. You just find out the values at the time under consideration yourself. Delta T, the time step. Delta T is divided by you. You can set time step yourself, 0.1, 0.2, up to you. So all the things here are well defined actually. All the things are well defined. You know M, you know C, you know K, you know delta T. So you can use this equation n times. You can use this equation n times. So for example, you firstly find out U1 based on the initial condition U0, U.0, and then you can use the equation to find out U1. Once you know U1, you can use the response of U1 to predict what happened on the next step U2, and then so on. At the top here, you can find out the whole history of the structures. Unknown displacement ui plus 1 at time I plus 1 can be obtained by successfully conducting this equation n times. This method is called explicit method because we use the previous response ui minus 1 to predict what happened on the next at time step I plus 1. We call it explicit in terms of those terminology. We use the previous response to predict what happened on the next. But to use this method, you have to pay great attention at the beginning at time equal to 0. When you go back to the previous picture here, this one, suppose this is time suppose this is U1, this is U0. According to central difference method, you need 2 previous time steps to predict what happened on the next. According to this picture, you need if you want to find out U1, then you need U0. And you also need to know one special term called U minus 1. What happened before time 0? Okay. How to find out u minus 1? That is what I mentioned on that slide here. You need some special values, u0, u minus 1, to evaluate u1. How to find out the expression for u0, u minus 1, this kind of things? You can go back to the definition of velocity and accelerations. Velocity at time equal to 0. Velocity at time equal to 0 is equal to u1 minus u minus 1 over 2 delta t. I'm just using the 5 different approximations and then put I equal to 0 into the equations. Same for accelerations. Slightly rearrange these two equations. You can express u minus 1 in terms of u0, u dot 0, u double dot 0. What are they? u0 is the initial displacement. U dot 0 is the initial velocity. Actually, you know what happened at time equal to 0, right? You know what happened at the beginning of the structures. Normally, we assume that it is at rest. We assume that the structure is at rest at the beginning. At rest means it has no displacement, no velocity, 0 and 0, okay? But at least you know what happened at time step 0. You can use it to estimate what happened for this special term, u minus 1, something before time equal to 0. You may use this equation to calculate what happened at this special time step, minus 1. The acceleration at time equal to 0 can be calculated using equation of motion. This is the equation of motion. u0, u dot 0 is some given initial conditions at time equal to 0. So this is some special treatment you have to consider at the beginning. You have to calculate the initial property to activate your calculations. Once you have this set of parameters, you can use it to find out u1. If you know u1, then you can use it to find out u2, u3, u4, and so on. Okay, after knowing the background, I give you one summary for central difference method. If you want to use central difference methods to estimate the dynamic response of a single degree of freedom system, then you can follow this table I obtained it from the textbook as shown at the bottom, Dynamics of Structures, a very classical dynamic textbook. You firstly evaluate some initial calculations, initial parameters, and then you can calculate the response at different time steps by repeating step 2 n times. Repeating step 2 n times, then you can get the whole displacement history for these structures. Depends on the skill you have. If you like, you may use, I think in the past you have learned some software language like C++ or C#, or you may learn Python. You have learned different programming language in the past. You may write a program to for this central difference method, and then you can click the run button. The computer will generate the whole displacement history for you. You may use computer programming techniques to implement this central difference method using different programming languages. But in this module, I don't expect you to prepare this kind of language. Instead, I will also use Excel, a very powerful software. Excel. We will use it to do our calculation together in Excel. Excel can also support programming. If you're familiar with Excel, Excel also supports programming language, but VBA. But in this module, we are not going to discuss too much about the programming language in Excel. I just use simple cells. I just use different cells to finish the calculations. I will let you know how to do it in our tutorial section today. Okay, I will work with you together to try to see how to implement central difference method in our tutorial sections. So right now we have some idea about what is central difference method. Central difference method is based on time stepping techniques. We divide the whole history into different time steps, and then we borrow one so-called central difference approximation. We try to express velocity and acceleration in terms of displacement in the previous time steps, and then we use it to estimate what happened on the next. The last one, central difference, Newmark's method. Newmark's method is also one numerical method based on the time stepping idea. But Newmark's method based on different approximation, based on different assumptions. Instead of using differentiations. Essential difference method based on differentiations. Newmark's method go in the other directions. By using different assumptions, you can set up another schemes to estimate the structural response. Let's have a look what is Newmark's method. Newmark's method based on different assumptions. The backgrounds are the same. We are going to solve our equation of motion at different time steps. But we found that there are too many unknowns. We can't solve it directly. That's why you have to make some assumption or approximations so that the problem becomes solvable. The what assumption we make? Under Newmark's method, we make assumptions on accelerations. We make assumptions on acceleration different from central difference method. What we make? Say for example, you may have a look of the picture on the left-hand side first. The left-hand side show you this graph x actually is equal to u. As I mentioned at the beginning, in some textbook they use x rather than u for displacement. X and u also mean displacement. Displacement of the structures. Some textbook use x, some textbook use u. Here I use x. I use the textbook using x for displacements. X double dot mean what? X double dot mean acceleration. X dot mean velocity. X mean displacement. So here show you displacement, velocity, and acceleration plot for two different time steps, ti and ti plus 1. I show you what happened between two time steps. Here is the acceleration, x double dot I, and here is the acceleration, x double dot I plus 1 at time step I plus 1. Okay, actually I just show you the coordinate for acceleration, velocity, displacement at between two time steps. And here we make assumptions. Say for example, you can assume that the acceleration between these two time steps is equal to a constant. You can use the average value between ti plus 1 to represent the acceleration at this time interval. That's why the title of this picture is called average acceleration, because we assume that the acceleration is the average value between two time steps. The average value is equal to x double dot I plus x double dot I plus 1 over 2 average. Okay, if you know the acceleration, you can use the acceleration to calculate the velocity. Right? You can use acceleration to calculate velocity. Right? Acceleration equal to dv. I use v for velocity. dt. You can integrate this equation. To get the velocity. Instead of using differentiation, you can do in the opposite direction. You can use integrations. Integrate acceleration, give you velocity. Integrate velocity, give you displacement. So Newmark's method start from the other directions. They make approximation using acceleration. And then they use integration, find out the equation for velocity, and then find out the equation for displacement. Okay. This is what the approximation behind Newmark's method. The first column, based on this assumption, assume that velocity is a constant between a time interval. So based on the same idea, Newmark suggests that, you can also make the other assumption if you like. If you don't like average value, then you can use linear accelerations. Instead of using a horizontal line, you can assume that the velocity, the acceleration is a linear function between two time instants. So based on this line, you can find out the equation for acceleration. And then same techniques. Integrate this equation, give you velocity. Integrate this equation, give you displacement. So based on different acceleration assumptions, based on different assumptions on acceleration, you can find out the corresponding equation for velocity and displacement. Okay, same idea. There are many, not only two. There are many approximation for the acceleration. I just give you two commonly used assumptions. And then Newmark proposed two Newmark equations. We normally call this Newmark equations. One is for velocity, the other one is for displacement. Okay, these two Newmark equations express using the velocity at I plus 1, displacement at I plus 1, using the previous velocity, previous acceleration, and using the current accelerations. Then what are they? Actually, they are the previous equations here, based on different assumptions of accelerations. Newmark generate all the scenario into two simple equations, one for velocity, one for displacement. And these two equations depends on two parameters. We call that Newmark parameters, beta and gamma. These two parameters reflect different assumptions of acceleration, just like the previous picture. If you use average assumption, average acceleration, then you can pick some specific value for beta and gamma. If you use linear acceleration, then there is another set of parameters for beta and gamma, just like here. If you want to use average acceleration, then gamma becomes 0.5, beta becomes 0.25. If you use linear acceleration, then beta becomes 1/6, gamma becomes 1/2. So for different assumptions, you have a specific value of beta and gamma. You can put it back into these two Newmark equations. Then you have the velocity and displacement. Newmark just generate two equations for general situations. We simply call this Newmark equations. Okay, what next? Next, you have to simplify the equation of motion to the form, just like central difference method. You have to do some grouping, find out, what I mean is that express ui plus 1 on one side, express the other u velocity acceleration on the other side of the equations. Here are some derivations. Say for example, the equation motion at time ti plus 1 expressed in this manner. All the things expressed using the terms I plus 1. Right. The acceleration, velocity, displacement at time equal to I plus 1. Also for the force. Based on Newmark equation 2, you can find out equation B on the previous page. Right. We show you two Newmark equations. We use equation B, help you to replace acceleration using the other properties, just like displacement, ui plus 1. Substitute the above equation into our Newmark equation A. Then you can get another equations for velocity. Acceleration, velocity, we have these two things. Now you can substitute these expressions into our equation of motions. Then you can simplify the equation in this manner. It looks quite similar to our central difference method, but pay great attention because k hat and p hat are different in Newmark method. They are different from the one that we saw before in central difference method. It's tricky because they're based on different assumptions, right? So it should look different. But we have a similar form. I plus 1, the displacement at the next time step can be calculated repeatedly using this equation. P hat over k hat give you the displacement, the new displacement. And then you can use it to predict what happened at I plus 2, I plus 3, I plus 4. Same technique. You just calculate k hat and p hat yourself. Here is p hat I plus 1. P hat I plus 1 is quite complicated because you can see that it depends on the loading at the current time step, depends on some parameter, beta, gamma, time step, mass, damping coefficient, these kind of things. And also, p hat depends on the displacement at time step I, the velocity at time step I, and the acceleration at time step I. So p hat depends on many factors right here. Depends on the displacement, velocity, and acceleration in the previous time step. But the outcome are similar. Repeatedly using this equation n times, then you can predict what happened on the next. You can use this equation to find out ui plus 1, and then you can use it to predict ui plus 2, ui plus 3, and ui plus 4. Just repeatedly using this equation based on the previous response, then you can get the whole displacement history. In this equation, we are using the current time step I plus 1 to estimate the displacement also at the same time step I plus 1. For this pattern, we call this implicit method in terms of the terminology. More important is here, if you want to implement Newmark's method, then you can follow this table obtained from the same textbook. You can use this table to implement Newmark's method if you like. Firstly, calculate some initial parameters based on Newmark's method, and then repeatedly using step 2 n times, then you can get the whole displacement history. The concept is quite similar to central difference method. But Newmark's method, you can see that Newmark's method involves more equations. So in terms of the implementation, Newmark's method is slightly complicated as compared with central difference method. Central difference method only have 2 equations, right? Let me check. Central difference method here only have a few equations in step 2, but Newmark's method have 4 to 5 equations, slightly more. If you have time, you can also implement Newmark's method in Excel or in the programming language that you are familiar with. I believe that some of you have learned C++ before. You may also use it if you like. Some example to just illustrate how you can use numerical method. Just some example that you know how powerful they are. This one, example 1, determine displacement for the following single degree of freedom system under sinusoidal force. In topic 6, you have learned how to find out the response of our structures under sinusoidal force. Here, the loading amplitude is 100 kilonewton. The loading frequency is 20 radian per second. I believe that all of you should know how to find out the steady state response of these structures. But instead of using our closed form solution, here you can build an Excel or a program using central difference method or Newmark's method to predict the structure response. Before implementing the program into Excel or the other programming languages, you may firstly calculate some initial parameters. In these structures, we know mass, we know stiffness, we know damping ratio, we know initial displacement, we know initial velocity. Based on mass and stiffness, you can calculate natural frequency, omega. And based on mass, frequency, damping ratio, you can calculate damping coefficient, C. In the picture, I did not give you C, but you can calculate C yourself based on damping ratio and natural frequency and the mass. You can set the time step yourself. Here, I set time step to a small value, 0.01. Use central difference method. And then we try to calculate some initial conditions, some initial parameters. Here you may do a simple substitution yourself to see what are the initial parameters. The initial acceleration, the special terms u minus 1, what happened before, times 0. And then calculate some parameter for central difference method, K hat, A, and B. They are based on mass, damping coefficient, stiffness, and the time step. All the values are given at the top. So you can find out the values. And then according to the central difference method procedures, you calculate P hat based on this equation. Depends on A, depends on B. P hat depends on A, B, the loading at the current stage, and also depends on the previous displacement, Ui and Ui minus 1. Apply this equation n times to find out the displacement at time step I plus 1. You can simply build an Excel like this The format is up to you. Different people may have different style to prepare your own spreadsheet. You may put some given information at the top, and then you may do some simple calculation for the initial condition based on the equation here. You can calculate those initial conditions, and then use this set of values to calculate the value at different time steps. You may start from time 0. Time 0, you know the force, you know the displacement u-1, you know the displacement u0, right? Because they're the initial values calculated before. u-1 here, u0. Using these values, using our central difference equation, you can find out p hat at time 0. And then using p hat, using k hat, you can find out u1. Then you finish the first row. Once you finish the first row, time 0, then you know what happened on the next time step, u1, right? This is u1. Then you can copy the value to the second row here. You can move u1, the answer, in the previous row right here, because in the next time step, at time step 0.01, this column, this value becomes the previous response, and then you can move this one to ui-1. So by moving these two cells to appropriate locations, now you can use these two new displacements to predict what happened on the next using the same equation. In Excel, it's just very simple. You just copy the equation along the whole column. In Excel, it's allowed you to copy the whole equation along the whole column. Then what I mean is that actually you just need to complete 2 rows in your Excel file. You just need to complete 2 rows in the Excel file. And then you can copy the equations along the whole column. Then problem solved. Okay, that's how you can use Excel. You can simply build an easy spreadsheet to do the calculations. You just need to focus on the first few rows. If the answers are correct, then you can copy the equations along the whole columns. Pretty easy. The last column in gray color, I just convert the unit from meter to millimeters. Up to you here. I just add one column here to show you mm. The unit is up to you. You may use meter or millimeter. Once you have a spreadsheet, just like here, once you have a spreadsheet, if you want to predict a structures under another loading, then you can just simply replace the loading to a new loading. Right? If you want to know what happened for structures under pulse force, under arbitrary loading, then what you have to do, you can use the same spreadsheet, but update the loading yourself. Then you can use this spreadsheet for all kinds of loadings. Okay, you can update this row yourself based on the given loading, pulse, arbitrary loading, side loading. Yeah, because central difference method apply for all kinds of loadings. If you have the response, you can also plot it. You can also plot it using Excel, the plot function in Excel. And then you can see from this response, you can see clearly which part is the transient response, which part is the so-called steady state response. This part is transient, and you can see a large displacement at the beginning, but finally those transient response will damp out because of energy loss. Finally, they will get to the steady state part. This is the thing that we learned in topic 6. Steady state and transients. Example 2, if you want to if we consider the same structures under a pulse loading, a rectangular pulse. As mentioned before, you can use the same spreadsheet. You just need to update the force function yourself. Under the change the P column here to the pulse loading. Then the computer will give you the displacement automatically. So it's quite convenient. I just do the same spreadsheet, and you can get the response of the structures. No need to do different update. You can see that we have a pulse, we have a force vibration period and free vibration period. What are they? When you take a look on the picture right here, the duration of the pulse is 5 seconds. The duration of the pulse is 5 seconds. That means within the first 5 seconds, there's force. Beyond 5 seconds, there's no loading. No loading, we call that free vibrations. That's why from the response plot, you can separate the response into two regions. Before 5 seconds, when there's loading, we call that underforced vibrations. And then beyond 5 seconds, there's no loading. For no loading, we call it free vibration phase. You can see that it's under the typical free vibration pattern. The amplitude decreases as time goes on. Finally, there are some remarks for you to think about. They are reference, not for examinations. As we mentioned before, time-stepping methods or numerical methods, they are general, powerful, because they can handle all kinds of loading. Well-divided loading, okay. Arbitrary loading, also okay. But please note that numerical method is not exact method. It's not exact because they based on some assumptions, just like central difference method, they based on central difference approximation. Newmark's method, we make assumption on acceleration pattern. So they are not exact values. If they are not exact, that means there will be some errors in your calculations. So when you use this kind of numerical methods, you have to pay great attention to this kind of requirements. Say for example, convergency. Time step is divided by u. You may set delta t equal to 0.1, 0.2, 0.3 yourself. But normally, the smaller the time step, the better the solution. But it means that if you use a small time step, then you may need to take a longer time to finish the calculations. So you have to balance the accuracy and the computation effort yourself. And you can also do a study. You can try to decrease the time step. You can decrease the time step. Say, for example, you use 0.1 at the beginning, and then you can try a smaller time step. And then you can check the response difference. Normally, when you use a small time, when the time step decreases, normally the numerical solution will closer and closer to the exact values. Okay, the response will converge to a single, the same solutions normally, which means convergency. Another issue is called stability. When you use computer to calculate the response of structures, it may involve some round-off error or the other numerical error. If you just consider one time step, the numerical error can be small when you just consider one time step. But you can see that we have to do many time step calculations, maybe 100, maybe 1,000, maybe even more time steps. So even though the error is small in one time step, but when you multiply the total time step, it may become a big error. So it comes to this idea called stability. Stability means your numerical solution should be stable, even though there is numerical round-off error. Some guy proved that there are some suggested limits how accurate can be achieved if you want to set a time step, as shown on the next slide. Accuracy is talking about the difference between your answer using the numerical schemes to the exact solution. For some method, for some loading like side loading, you know the exact solution, like for side loading. So you can use this kind of well-divided loading to check the accuracy of your method, Newmark's method or central difference method, etc. As mentioned before, about stability, some guy derived some suggested time step. You may think in this way. Some guys suggest that there are some suggested time step to make your answer become more accurate, rather than having a large numerical problems. For central difference method, some guy proved that your time step over the period of your structure should be lesser than 0.32. You may change this equation a little bit. You can move period to the right-hand side if you like. So you can express stability in terms of a factor times structural period. Some guy also derived the limit for Newmark's method. It becomes these complex equations. But generally, for structural dynamics, we will set our time step lesser or at least equal to per one time the vibration period of a structures. For structural dynamics, normally this boundary is okay for all kinds of numerical methods. Okay, normally per one is okay. Per one times the structural period. If you consider earthquake analysis, then you can use a slightly smaller delta t, say for example 0.01 for earthquake analysis. This one is quite useful, I think, these suggestions, because time step is defined by you. If you have not much experience in using this kind of numerical method, I believe that this kind of suggestions can help you to start up your analysis. So the end of chapter 7. This is a relatively short chapter, numerical methods. Okay, let us have a short break right now, 5 minutes. After the break, I will mention something about the assignment and also the quiz. Testing. Okay, let's begin our discussions. Before the break, we complete chapter 7, numerical method. And then this moment, maybe we can talk about some extra issue other than the natural materials. According to Moodle, update some information on Moodle. Say, for example, I've uploaded marks of assignment 1 on Moodle. I've uploaded the 70,000 assignment on Moodle as well. You may have a look. I've uploaded the equation sheet for the quiz on Moodle for your reference. Because in the quiz, you're allowed to bring one A4 paper. You can put down notes, you can put down equations, example on this A4 paper. This one is prepared by you. This one is prepared by you. You have to, if you like, you may prepare your own A4 paper, put down some equation, example, etc. In the quiz paper, I will also give you some standard equations. They are all found in this equation sheet. In the quiz, I will give you one simple equation sheet. At least you have something to follow. But other than that, you can prepare your own A4 paper. You can write down example equations on your A4 paper. And also, I upload assignment 2. Assignment 2 on Moodle. So the due date of assignment 2 is the end of November. The end of November. So you still have a long time to complete assignment 2. What about assignment 2? This is assignment 2. Assignment 2 is, in terms of the difficulty, I think assignment 2 is easier as compared to assignment 1. Because I just focus on single degree of freedom system in this assignment. There are totally 4 questions. Question 1, we talk about a single degree of freedom system. You know the mass, you know the stiffness, you know the damping ratio, you know the force. Just ask you to find out the steady state response of this single degree of freedom system. Right. We mentioned this steady state displacement response many times. UST, RD, and then times and psi function. So you know exactly the the solutions. You just use it and substitute those parameters into the equations. So it's pretty straightforward. And then question 2 asks, part 2 asks you to plot RD versus beta plot. We call the frequency response plot. In the notes, I showed you some example about frequency response plot. Here, just ask you to simulate yourself. Very easy. And then testing you whether you understand so-called resonance. You in part 3, you're asked to find out the displacement at resonance stage. Resonance means what? At resonance means loading frequency equal to the natural frequency of the system. Just testing you this knowledge, resonance. And then calculate the equivalent static force. Part 5 asks you to find out the total force transmitted to the support, which means using the idea of transmissibility that we learned last time. Transmissibility. And then part 6 is quite special. Part 6, if the load removed suddenly, if this harmonic force removed suddenly, I ask you to find out the displacement function again. Find out the displacement response again. I give you the tips as well. If the force is removed, that means it is under free vibrations. I give you the tips here. You know the free vibration response, so part 6 is also direct using our equations. Question 1, pretty straightforward. Testing you the idea, mainly harmonic vibration and some free vibrations. Question 2, even simpler. Question 2 asks you to use the approximate method that we introduced last time to estimate the response of the same structures under a square pulse. We introduced approximate method last time for pulse loading. Just use it. I think only a few steps for question 2. Very straightforward. Question 3. Question 3 testing the idea about numerical method. Here I select central difference method because this one is more easy to implement. Central difference method. You firstly make your spreadsheet, Excel spreadsheet for central difference method, and then calculate the response of these structures under this loading. this is this is a loading with some well-defined values. You cannot express the loading mathematically, but you can find out the coordinate at different points easily. So you can use Excel to solve this problem. I give you some suggestion here. In your Excel file, you don't need to send me the Excel file. No need. You may use print screen in your computer to show me part of your program, part of your Excel. Do not show me all the steps, because your Excel may involve many times steps, 100 or 1,000 times steps. Don't need to show me all the steps. Okay, you can just show me part of it. Maybe the first few seconds using print screen or the other technique. Show me part of your Excel. And then you ask to plot the displacement time graph, the displacement response up to 20 seconds. I can check your response using this displacement time graph. Okay, very easy. Build a spreadsheet and then consider these special loadings. Question 4 actually asks you similar things. The same structures under earthquake. Under earthquake, the equation of motion can be expressed using these equations. You can see that under earthquake, the loading is equal to -m times the ground acceleration history. On Moodle, you can find out the ground acceleration history for this epicenter earthquake. So the acceleration time mass give you this equivalent force. If you know the force, then you can use the previous Excel, change the force column. Then your Excel will give you this the new displacement. Okay, so this one is also not that difficult. Once you have the Excel in part 3 and in question 3, you can use it in question 4. Okay, these are something about assignment 2. And then we have a formula sheet. We have a formula sheet. This formula sheet will be provided in the quiz. This one will be provided in the quiz. I just attached this formula sheet after the question paper. This formula sheet basically involves some equations for Stevens method, which are relatively difficult to remember. I give you the thrust matrix and some force, some fixed end force due to fabrication error, due to temperature change. And also I give you the beam matrix, the fixed end moment calculation. And finally, I give you the frame matrix, the general format and some special format for horizontal frame and vertical frame member. So in your own notebook sheet, you don't need to put down the matrix, I think, right? Because I give you already. In your own notebook sheet, you can put down the remaining equations. Actually, there's not much, because we just test you up to topic 5. Topic 1, 2, 3 are covered right here in the formula sheet. Okay, anything you want to ask me regarding the quiz or the other thing? About the quiz, about our quiz, the full mark of the quiz is 100, and then around 70% will be something related to Stevens method. $70 marks will be allocated for Stevens method, and then the remaining 30 marks will be allocated for dynamics. Syllabus method covered topic 1 to topic 3. Topic 1 to 3. Well, dynamics, it just included topic 4 and topic 5, up to 3 variations. So there's not much contents in dynamics. Right? And there are 2 questions for syllabus method. There are 2 questions for syllabus method. 1 question for structural dynamics. So totally there are 3 questions in the quiz paper. And the quiz is a face-to-face quiz. So next time you should come back to the campus and have the quiz. Reserve some time when you need to come back to the campus, because you have to, when you enter the campus, you have to finish those missing parts, etc. It may take you some time to do so. And also have to consider the transportation issue, because you may need to wait for some time for public transport. So reserve some time for you, okay? Yourself. For syllabus method, I suggest you, if you have no time, if you are busy, I suggest you may focus on trust and beam if you have no times, okay? For syllabus method, if you have no time, I suggest you may focus on trust element and beam element. For frame, you may study later. For dynamics, actually, I have only 1 topic that can assess you, the free variation. Topic 4 is about formulation. There's no special issue, I think. It's also, it helps you to understand how to formulate the equation of motion. But in terms of calculation, it's more related to topic 5, free variations. One question for free variations. So there are 2 questions for syllabus method. 2 questions. You can, if you have no time, you can study the truss and beam proofs. There is 1 simple question and 1 lengthy questions. Simple questions mean I sometimes, for some simple questions in syllabus method, I will give you the structured syllabus matrix for some simple questions. So you can directly use the syllabus matrix to calculate the response. That's why I call that simple problems. For complicated problem, you have to construct the syllabus matrix yourself, and then use it to find out the response of structures. Okay. So I hope it's helped you to understand what you will encounter the next week. There are totally 3 questions in the quiz, 2 syllabus method, 1 dynamics. For syllabus method, I believe you know what will be appeared in the quiz paper. And then dynamic, I give you quite a lot of examples for structural dynamics. You may refer to the examples in the notes or in the tutorial 5, something like that. In Moodle, I also uploaded 1 revision notes for you. If you have time, you may also have a look. This one, you may have a look of this PDF. I summarize some key things that you may need to be aware of. Okay. Oh. Anything you want to ask me? Otherwise, I will go to tutorial 7. Everything clear? So far, so good. 冇問題。If you have no questions, then thank you for the response. If you have no questions regarding to the quiz, then what I can say is that good luck. I think you have a quiz tomorrow as well, right? Geotechnical engineering and foundation. Also good luck for that quiz. Yeah. Just review the notes and example. I believe that should be okay. So let us go to our tutorial sections. Let us go to our tutorial sections. Tutorial 7. Tutorial 7 is also help you to solve our assignment 2 problem. Let me share the screen with you. Tutorial 7. Tutorial 7 will focus on impulsive loading and numerical methods. There are 2 questions in this tutorial 7. One is about impulse force, the other one is about numerical methods. Using Newmark's method, particularly. Using central difference method, particularly. And question 1. Suppose we have a structure. I give you the mass, I give you the stiffness. You know M and K. In these questions, you are asked to find out the maximum response. Here, the maximum response means the displacement and the base shear force and the overturning moment at the base level. When the structure is under horizontal force, there is base moment, there is base shear force and overturning moment, and also the structure will display horizontally. So in these questions, you are asked to find out the response of these structures under the given pulse loading. The pulse is trapezoidal shapes. When you see a pulse loading, in this module, when you see a pulse loading, then you can use the approximate method because we just introduced that method to handle pulse loading. In theory, there are different methods to handle pulse loading. You may go back to topic 6. In topic 6, I introduced there are different ways to handle pulse loading. Some based on mathematics, you can solve the differential equation directly. Some based on techniques so-called the Helm integral. Today, you may also use numerical method if you like. You may use the method or central difference method. But right here, I would like to use the approximate analysis, approximate method for pulse loading. So to use the pulse loading, to use the approximate method, there is one assumption we have to check. The assumption is that you have to make sure that the pulse is a short pulse. What is the meaning of short pulse? Short pulse means the pulse duration. Maybe I call this TD. The pulse duration, TD, over the natural period of the system, Tn, should be less than or at least equal to 1/4. That is the requirement for using approximate method. If the ratio beyond this limit, then you have no choice. You have to solve the equation directly using integrations or using the other techniques. But if you find that this ratio less than the limit, 1/4 or 0.25, then you're allowed to use the approximate method. So how to use the approximate method? Firstly, you have to find out the period, because in this problem, I did not give you period. I give you mass, I give you stiffness, but there's no period. So you have to calculate period yourself. Period. You may start from frequency. Frequency omega n, natural frequency. By definition, it is equal to square root k over m. Square root k over m. Be careful about the unit. Use standard units in the calculations. Newton per meter for series, kg for mass. I use standard units here. You have to make sure that unit consistent to each other. And then we found that the frequency is equal to 3.14 radian. Period. Period equal to 2 pi over frequency. So 2 seconds. And then you can check the requirement. TD is the duration of the pulse. According to the picture on page 2, the duration of the pulse is 0.3 seconds, 0.3. From the picture here, you can see the pulse durations, 0.3 seconds, 0.3 over period, give us 0.15. It seems that this ratio less than our limit, 0.25. So you are allowed to use the approximate method. To use the approximate method, you just need to calculate the area under the pulse loading. Mathematically, you are asking to find out the integration of the PT graph. But you know integrations mean area. You can find the area under the PT graph. Area of these trapezoidal regions, I believe that all of you should know how to do it, right? The top length plus the bottom length times the height over 2. I believe that you can calculate the area yourself. Area of this trapezoidal. I found that it is equal to 44,480 Newton-second. Once you know the area, you can use the approximate formula given in the notes. The maximum displacement is equal to the pulse area over m over frequency. We know the pulse area, we know the frequency, we calculate at the beginning. The mass is given. So by this simple calculation, you can get the maximum displacement. Maximum displacement is equal to 0.0156 meter. If you like, you may change to millimeter if you like. Up to you. So you know the maximum displacement. For dynamic problems, normally you have to firstly calculate the displacement response force first. For dynamic problem, we firstly calculate the displacement first. That's why in the notes I give you many equations for displacement functions under free vibration, under harmonic vibration, under pulse vibration here. Once you know the displacement, you can use it to estimate one very useful quantity called equivalent static force. Equivalent static force means the static force that gives you the same displacement. Okay? Equivalent static force means the static force that gives the same structure, the same displacement, u0, which is equal to 0.0156. Then what is the value of this equivalent static force? By definition, it is equal to the stiffness of the system times the displacement. Stiffness times displacement give you force. So Fs can be calculated using this something like Hooke's law. Stiffness, we know it, given in the problem. Displacement, we just calculate above. Divided by 1,000, just for unit conversion, convert from Newton to kilonewton. 1,000 is for unit conversions. So we found that the equivalent static force that gives the structure the same displacement is equal to 139.7 kilonewton. After finding this equivalent static force, we can treat this structure as a static problem, equivalent static system. We can treat this as a static system. For static system, then it becomes easy. The force is now equal to 139.7 kilonewton. For static, you can directly apply equilibrium equations. You can find out the base shear force. You can find out the overturning moment easily, right? The base shear force, VB. The base shear force, VB, by horizontal force equilibrium, it is equal to the equivalent static force, 139.7. Horizontal force equilibrium. Moment equilibrium. Overturning moment equal to the force, 139.7 times the height. The height is 5 meters.